We will now state and prove the crossing lemma. Already in 1973, Erdős and Guy conjectured that the number of crossings in a graph is at least omega of m to the 3 divided by n to the 2. And in 1982, it was proved by Leighton and independently by these four authors that this is in fact true, and that we can reach a constant of 1 divided by 64. Asymptotically, this bound is sharp, so we can draw every graph with order of m to the 3 divided by n to the 2 crossings. The constant, however, is not known yet. This result was not really well known until 1997, but since then there has been some work on it, and I will show you the proof from the book for this result. This was by Chassel, Sharia and Welz. This is a very nice, short, concise, probabilistic proof where we get this bound from. This is not the best known bound at the moment. This was improved by Ackermann with many intermediate steps to 1/29, but we don't know anything better yet. So, the crossing number says for a graph with n vertices and m edges, and at least 4n edges, the number of crossings is at least 1/64 times m to the 3 divided by n to the 2. To prove this, we consider a minimal embedding of G. So we assume that we have a drawing with a minimum number of crossings. We now fix some number p between 0 and 1. This is our probability. And for every vertex in the graph, we will flip a weighted coin. So with probability p, we will keep the vertex, and with probability 1 minus p, we will throw it away. That gives us an induced subgraph GP. Now we have random variables for the number of vertices, edges, and crossings in this graph. And we want to figure out the expected value of these random variables. For that, we will make use of lemma 2 of the first bound that we had. There we showed that the number of crossings we have is at least number of edges minus 3 times number of vertices, plus 6, but we will drop that for now. So the expected number of crossings minus this is at least 0. Now, what is the expected number of vertices and what is the expected number of edges in this graph? Can you figure this out? Well, with probability p, we keep a vertex, we do this n times, so we have expected p times n vertices. And for the edges, well, we still have it if we have both of the vertices. And the probability that we have both of the vertices is p squared. What about the number of crossings? Well, for a crossing, we need 2 edges. So a fixed crossing we still have if we still have both of those edges. So the probability that we still have a crossing is p to the 4. We need either both edges or we need all 4 vertices. Now we want to get a bound for the crossing number. We first use this part here, and with linearity of expectations, we get this formula. Now we will plug in those numbers. So here, p to the 4 crossing of g, p squared m, 3pn. And we want to solve this for number of crossings. So we move all the stuff on the other side and divide by p to the 4. We get this bound here. We will split this term into the first and the second part. The first here is m divided by p squared. The second is 3n divided by p to the 3. So this gives us a lower bound on the number of crossings we have, depending on the probability that we choose. And now we will just choose the probability as 4n divided by m. And if we plug in this magical number here, then this first part is 4n squared divided by m squared. So we have m to the 3 here, and we have 4n squared, which is 16n n squared here. And on the right side, this m to the 3, we go to the top, and we have a 4n to the 3 down here. We will remove one of those n's, and 4 to the 3 gives us 64. And now the denominator is almost the same. To get them on the same, we have to multiply this by 4, and then we have m to the 4 in the numerator, and 64n squared in the denominator. And that's already the proof.